Hello, everyone. Welcome to our webinar today at Statistics Solutions. During our webinar today, we are going to cover how to conduct and interpret correlation tests. My name is Justin D'Souza. I'm a quantitative specialist here at Statistics Solutions. We're going to go through the entire webinar first, and we'll do a Q&A session at the end. So if you have any questions, you can type them into the chat box or the Q&A box, and we will review those at the end. My colleague Sierra is going to provide some hyperlinks in the chat box. If you have any questions about the services we provide, you can schedule a free consultation with us. And we'll send everyone a copy of the PowerPoint and a copy of the webinar as well. All right, I'll give an overview of the services we provide at our company. Then we will discuss how to select an appropriate correlation test. I'll give a demonstration in SPSS, how to conduct correlations, and then we'll conclude with a summary and a Q&A session. On this slide, you can see all the parts of the dissertation journey that we assist with. We have literature review specialists at our company, and we have methodologists, both quantitative and qualitative. So if you need help framing research questions, picking a theoretical framework, identifying your data analysis plan, we help with every part of the dissertation journey. We can also crunch your numbers for you. So if you send us your data set and your proposal and any scoring instructions for your tools, then we can provide a results chapter to you in APA format, either quantitative or qualitative or mixed methods. And then we assist with the discussion and PowerPoints for your defense. And we can help to form a journal publication. Some students work on a journal after their dissertation, so you can condense your dissertation into a journal, and we can assist with that step. If you have any questions, you can give us a call at 727-442-4290, and you can also check out the links that Sierra has posted in the chat box. You can schedule a free consultation using one of those links. Okay, so today we're discussing correlations, but before we get to there, it's important to understand parametric and non-parametric statistics. Most analyses branch into one of those two families, parametric or non-parametric. Parametric statistics are based on assumptions about your population. Usually, the most predominant assumption is that your data follows a normal distribution. So I'm sure everyone here has seen a bell-shaped curve at some point. Your variables of interest usually need to be normal. They need to follow a normal distribution when you run parametric techniques. And this usually involves looking at continuous variables, which we will discuss on the next slide. Non-parametric techniques are not so strict on assumption checking. Okay, so you don't necessarily need to have a normal distribution to run non-parametric techniques. The normality assumption is something you'll see very often. It's one of the most prevalent assumptions you need to verify, and there are many ways to check for this. You can run a Shapiro-Wilk test, you can run a Kolmogorov-Smirnov test, and you can look at skewness and kurtosis. Those are more objective cutoffs. Does my data follow a normal distribution or does it not? But you can also look at more subjective determinations. If you look at scatter plots or histograms, you can determine visually, does my data follow a normal distribution? If the assumption is not supported for normality, then you might need to shift to a different technique. And that could be a non-parametric technique as an alternative. One of the things you can use to bypass normality is using your sample size. If you have a very large sample size, you can use something called the central limit theorem to justify proceeding with parametric techniques, even if your data is not following a bell-shaped curve. I put a citation here, Howell 2013. He indicates that violations of normality are not problematic when your sample size exceeds 50 cases. Then we go into levels of measurement. Okay, so this is also really important when you're figuring out what is the best test to run. We have continuous, nominal, and ordinal variables. Continuous is exactly what it sounds like. It's when a variable falls on a continuum or a scale. Examples of this include test scores, standardized test scores, temperature, weight, composite scores from the survey. If you're using a Likert scale survey, many times you average them all together or you take a sum. Once you've taken a composite of your Likert items, that variable is now continuous. Nominal items or nominal variables have distinct categories or discrete categories. Examples of this include gender, ethnicity, or passing and failing of an exam. So if you use the actual score on a test score, that is continuous. But if you put those scores into high and low categories, passing and failing, then that would be nominal. Ordinal variables are similar to nominal. It's a subset of a nominal variable, but there's a distinct categorization. It goes up a hierarchy. So you have ordered or ranked options. So something like education, that goes up a natural progression with associates, bachelor's, master's, PhD. Or if you're using a single ordinal item on a survey, like a Likert scale, just one item, that would be an example of an ordinal variable. Okay, so looking at correlations, which are used when you're looking at the association. Typically, you don't have to have independent, dependent variables. You just need to have two variables of interest. And we branch this into parametric techniques and non-parametric techniques. So the first one is a Pearson correlation, and this is used when you're looking at the relationship between two continuous level variables. So if you're looking at the relationship between, GPA and a specific test score, you could use a Pearson correlation for something like that. A point biserial correlation is used when you have a dichotomous variable, so a two-level variable, but also a continuous variable for your second factor, okay? So what is the relationship between gender, that was just male and female, and GPA? That would be an example that you could use a point biserial correlation. Non-parametric techniques involve, if you don't have continuous variables. The first one is a Spearman correlation. So this can be used when at least one of your variables is measured ordinally. So what is the relationship between education level and GPA? You could use a Spearman correlation there because education is ordinal. Associates, bachelor's, master's, PhD. It's not continuous. And then the final non-parametric technique is a chi-square test, okay? And this is used when you have two nominal level variables, two categorical factors. Something like, is there a relationship between gender and passing and failing an exam? You have males and females, and then you have passing and failing. So you could do a chi-square test in that example. When you do correlations, this is the typical path that you should follow for interpretation. Okay, so first you look at the p-value, and that's going to tell you if you have a significant association. And the most conventional cutoff for that is using a p-value below 0.05. Then you can apply Cohen's standard to interpret how strong is your correlation. And you can see the different cutoffs. So if the correlation coefficient is between 0.1 and 0.29, you have a small association. Between 0.3 and 0.49, you have a medium or a moderate association. And any coefficient larger than 0.5 represents a large or strong association. Okay, so looking at the Pearson correlation first. Again, this is a parametric technique, and you need to have two continuous variables. The first thing you should do is check for normality. And if normality is not supported, then use your sample size to justify proceeding if it's sufficiently large, or shift to a non-parametric technique, Spearman correlation. Okay, and then I put the instructions in SPSS how to conduct this. We'll go through an example shortly. I just want to go through all the different options. So a point by serial correlation, again, this is parametric, and you need to have a dichotomous or a binary variable and a continuous variable for your second factor. And there isn't necessarily a non-parametric alternative to this, not a clean one. So because this has a continuous variable, you should check for normality again. But if normality is not supported, then you need to use your sample size to justify or shift to a Mann-Whitney test. And I can show you an example of that as well. A Spearman correlation, this is the first non-parametric that we have. You need to have at least one variable that's ordinal, or if you proposed a Pearson correlation and the assumption of normality is violated, then you can run a Spearman correlation as a backup. And then we have a chi-square test that was used to look at two nominal level factors. Okay, so let's look at an example here. I do see some familiar names that have joined the webinar today, which is great. Oftentimes I use the same spreadsheet. So we have car models. Each row represents a different car. And you can see different statistics that were generated. We have mileage, we have the number of cylinders, we have the weight of the car, what type of engine is it. So say we're going to run a Pearson correlation for here. Kind of split up the PowerPoint in the SPSS file here. So then if we do, say our research question is there a significant relationship between the mileage of a car and the horsepower of the car? First, you would need to check for normality on that. So you go to Analyze and Descriptive Statistics and Explore right here. And I would put in mileage and horsepower in this right box. Then go to Plots and check mark this box right here, normality plots with tests. I would also check mark histogram right here and then click OK. This will take a few seconds. It reports quite a lot. Okay, so this is what we have. And the first thing it's going to do is check for normality. Now, there are two ways to do it. Just go with whatever your professor or your chair prefers. The math is fairly similar, but most professors have a preference. I tend to go with the Shapiro-Wilk on the right here. And significance on this test is actually not ideal. So you want ideally to have a p-value greater than 0.05 on this test. And we can see that for mileage, we have a p-value greater than 0.05. However, for horsepower, it's right below that threshold. It is significant, meaning that horsepower doesn't quite follow a normal distribution. And we can see that in the histogram here. This doesn't resemble a bell-shaped curve. So what I would do is run a Pearson correlation here, but then run a Spearman correlation as a backup. And so we go to Analyze and Correlate, and then Bivariate right here. And we're going to put in horsepower and mileage right there. Okay, and then click OK right here. Good. So this is going to generate a correlation. And it might be a little small to read both, but I want to have the PowerPoint here as well, because this is the process for interpretation. Let me just make it big for a second. So first we look at the p-value. Do we have a significant p-value? Then we interpret Cohen's standard. Okay. first thing we'll look at is the p-value, which is right here. The significance, that is our p-value. It is below 0.001. Cutoff is 0.05 conventionally, meaning, yes, we do have a significant relationship between horsepower and mileage. Then we need to interpret the correlation coefficient, and this is where we use Cohen's standard. The correlation coefficient is this value right above the p-value, negative 0.776. A couple things to consider is that for one, it's a negative value, meaning we have an inverse relationship. As horsepower increases on a car, the mileage tends to decrease, which makes sense intuitively. And then you interpret how strong is it? And it's 0.776. So you compare that 0.776 to this citation, which says anything above a 0.5 represents a large or a strong association. So collectively, we have a significant relationship between horsepower and mileage. It is an inverse relationship, meaning that as horsepower increases, mileage tends to decrease. And vice versa is true as well. As mileage increases, horsepower tends to decrease. And the correlation coefficient indicates a strong or large association. This was the Pearson correlation. Now remember, normality was not supported here for horsepower. So I would run a backup, go to correlation and bivariate. It's the same table, but you just need to check mark this box right here. And this is a Spearman correlation now that is not so strict on having a normal distribution as a requirement. And this also shows a similar relationship. We have a significant relationship. We have a negative value indicating an inverse association, and it's a strong correlation. Okay, so then the next, we just covered Pearson correlation and Spearman correlation. We can do a point by serial as well. I don't see this too often, but it's good to know just in case. I would just do a t-test instead of a point by serial. To do a point by serial, we need to have a dichotomous variable or something that is binary. And we have a couple of those here, engine type and transmission type. Before we run it, we need to convert this to numbers. So we need to have just ones and zeros or ones and twos. You can't run it with a categorical variable. So I'm going to add a variable right here and sort this column like this. And we'll make automatic a 1. Make manual a 0. And let's do it the opposite way. Let's make manual 1. Usually the less frequent category is coded higher. So there's fewer manual cars. So manual will be 1. Automatic is 0. And let's give this a name. So this is transmission type recoded. 1 is a manual, 0 automatic. And then we'll go to analyze, correlate, and bivariate. This one's real easy. You just check mark Pearson correlation. The math is done the same for a point by serial correlation. So there isn't a specific option for that in here. You just check mark Pearson correlation. And let's put in transmission type here. And I'll take out mileage, or I'll take out horsepower. This is a point by serial correlation between mileage and transmission, and it is significant. Okay, so we have a significant correlation, and what it shows is that manual cars, which were coded 1, automatic was coded 0. It shows that manual cars tend to have higher mileage. So it's a positive relationship, and it's a strong association. And going back to our previous example, we did horsepower and mileage. Another thing I would do is run a scatter plot. So if you go to graphs and chart builder here, you can run a scatter plot to look at the relationship visually. Okay, so mileage goes here and horsepower goes here. And then you can see, there is clearly a negative trend here. As mileage increases, horsepower tends to decrease. And you can even draw a summary line for this. The fit line at total, that is going to give you the summary trend for the relationship. Okay. And the final example we have is a chi-square. That is when you have two categorical factors, as we do for engine type and transmission type. Okay, so you go to analyze. There's a couple different ways to do this. You can go to analyze, descriptive statistics, and crosstabs right here. And then put in engine type and transmission type. Then go to statistics right here and check mark this box, chi-square. That's pretty much it. Okay, so this is going to generate a chi-square, which is cross tabulation between two categorical factors. So we can see that, 7 cars that were automatic also had a straight engine. We had 6 cars that were manual that had a V-shaped engine. Ultimately, there is not a significant relationship here. Okay, so we don't have a significant association between engine and transmission type. All right, so those are the four different examples of correlations. We had Pearson, Spearman, point by serial, and chi-square. So first, you have to frame your research questions, right? You need to do that fairly early on in the process, and then pinpoint what are the levels of measurements of your variables. Are they nominal, continuous, ordinal? Do you have a large sample size? If you do, then you can proceed. That gives you a lot of ability to bypass assumptions of normality. And then check for the assumptions of your tests and then run the appropriate test. Okay, do we have any questions? You can type them into the chat box or the Q&A box. So Likert scale, I do see a question that was fairly early on. And that's a great question. So Likert scale, let me move it to a Word document here. I'll move all the questions to a Word document. So the first question we have is Likert scale was under both continuous and ordinal. Which is it? So it depends. If you're looking at one Likert scale item at a time, that is ordinal. If you're examining one Likert scale item, but many times with surveys, you have to take an average of them, or you have to take a sum of all the Likert scale items. And once you've done that, that resulting variable is continuous. Okay, so for example, if I just had one strongly agree to strongly disagree item, this is ordinal. If I had, the MLQ, for example, or the JSS for job satisfaction has 10 Likert scale questions. If you examine each of those on their own, it's ordinal. But if you compute an average from all 10 items, resulting variable is going to be continuous. Okay, does that make sense? So it depends if you're creating an overall score or not. That will make the determination on, is it ordinal or is it continuous? Okay, so we have a question from, sorry if I can't pronounce your name correctly, Bamidel. So let's see. So she asks, I'm doing an associative correlation. One of the research questions is, if and to what extent does financial self-efficacy have a greater correlation with financial behavior than financial knowledge among working adults? It sounds like everything is potentially continuous. It depends on if you're using single items to measure these things. Are you using one item or are you using multiple items? If it's one item, it's potentially ordinal or even nominal. But if you're averaging or summing together multiple items to capture self-efficacy and financial behavior and financial knowledge, then it would be continuous. So it's very specific as to how the survey was built. Okay, we have a question from Miss Fowles. And she asks, so how would one consider the correlation or association between per capita expenditures of a budget and communicable disease cases in specific geographic areas or zones where the populations in each zone are different sizes? This sounds like more than just correlations to me. Between capita expenditures of a budget. Yeah, this one's a little more tricky. I don't know if just strictly correlations is going to be enough. It really depends how the data set is organized. Like, what would each row represent? Is it a different zone or a different geographic area? It's possible you could run correlations. You know, if expenditures, that sounds like it's a continuous variable. Budget could be continuous. Disease cases could be continuous. It may be possible just to run correlations. The research question sounds a little more advanced to me. So you might have to do regressions or maybe even ANOVAs to look at differences by geographic areas or zones. So there could be a number of possibilities here. We have a question from Rebecca. Is there a different webinar on how to do correlative testing on more than two variables? I've done webinars on regression models. And in that, you know, correlation and regression kind of go hand in hand. And you could have more than two factors for that. But also a less used correlation is if you do partial correlations here. So partial correlations, you can have three or more variables. So you have two variables of interest, and then you have an additional factor that you can control for. So that could be an option for you as well. Okay. From Ms. Fowles, each row would be an expenditure by N. Yeah, it's possible that you could just do correlations for this. It sounds like everything is numeric, but it gets a little tricky when you're looking at specific, if you're trying to compare across areas or zones. I don't know if correlations will be enough at that point. You might have to do ANOVAs potentially. Okay, we have a question from Rebecca. Can you describe the theoretical difference between correlation and regression testing? How does a regression compare significance levels? So the terminology, there's correlation designs, correlational designs, and underneath this branch of correlational designs, you have correlational analyses. That's what we covered today. So, you know, Pearson, Spearman, and all of that. Then you also have regression analyses. It's a little confusing, the terminology. So underneath correlational designs, you could be running regressions because you're looking at the associations between different things, but specifically, this is looking at prediction. Okay, so for a correlational analysis, like a Pearson or a Spearman, I mentioned earlier, you don't have to have independent and dependent variables. You just need variables of interest. And it's telling you the two-way association between your factors. When you do regression analyses, you need to have a clear independent and dependent variable. You need to know, does variable A predict variable B, essentially? Does that make sense? We have a question from Emidel. How would I know if my variables are nominal or ordinal? Nominal is going to be anything that is categorical. Ordinal can also be categorical, but there's a natural hierarchy or a natural progression in how the question responses are. Education's the best example I can give. Associates, bachelor's, master's, PhD, it goes up a ladder. Or a single Likert scale item. Strongly agree, neutral, disagree, strongly disagree. A single Likert scale item is also ordinal. Something nominal would be ethnicity, gender, things like that. Follow up from Rebecca. When is a t-test considered? So a t-test is considered when you're looking at differences. Okay, so a t-test is used to analyze for differences. That's the key word. Differences in a continuous variable. Between two groups and females, something like that. That's when you do specifically an independent sample t-test. I see my internet says it's a little unstable. Hopefully you can still hear me. So an independent sample t-test is used to look at differences in a numeric factor between two groups. There are multiple types of t-tests. You know, there's also paired sample t-tests. That's looking for pre and post differences. Continuous variable. There's also a one sample t-test that's not used often, but that's an option as well. All right, some good questions. Do we have any other questions? Question from Rebecca. So would it be common for a dissertation to use multiple tests? Yes, I see it very frequently. Sometimes it's just one test, but sometimes the research questions can't capture everything, or you can't use one analysis all the time to address every question. So you might have a combination, and that is very frequent. Yes, so you mentioned with demographics first, running t-tests, and then correlative for multiple variables. Sounds good. I'm not sure I understand the last question, Emidel. If my variables are continuous, can my variable be ordinal or nominal? These are all three different things. So continuous, strictly numeric, ordinal, something like education, nominal, something like ethnicity. Yep, thanks for joining, Rebecca. Do we have any other questions? All right, thanks for joining, everyone. Come join us for our future webinars. We'll send a copy of the PowerPoint and the recording, and let us know if we can be of any assistance. Have a great day.